So this is our last and final assignment, and that is nuclear physics. In this tutorial, our goal is to understand nuclear physics, to understand nuclear fission, which allows us to understand enrichment, because enrichment is the process uh, of, 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 of creating an atomic bomb, right? So fission will help us understand atomic bomb or even the nuclear power plant. And also nuclear physics will allow us to, our goal is also to understand fusion, which allow us to understand the secret of sun, so that we can become type 0 civilization. We are right now type 0 civilization to all the way type 2 civilization, right? Type 2 civilization is the civilization that's smart enough to harness all the energy coming from the sun, right? uh, to use all those energy. And type 3 civilization would be the civilization is smart enough to harness all the energy coming from the black hole to use to serve their need. Right now we are type 0 civilization because our physics is only 400 years old. The day Sir Isaac Newton, right? Look at the sky, saw a moon and said, if apple fall, does the moon also fall? Our physics is 400 years old, but within 200-300 years we're probably going to move from type 0 civilization to type 1 civilization, if some of you end up become next Isaac Newton or Albert Einstein. That's the hope, and that's the goal of this assignment. Okay, so what is the goal of this assignment? The goal of this assignment is not to also help you to win Einstein on Friday. Thursday is Einstein 9 and Friday is Einstein competition final. But the main goal is to allow us to understand the fusion. To understand the fusion, you understand secret of creating an atomic bomb, or more importantly, nuclear power plant. And the fusion going to allow you to understand the secret of the sun, so that we can become interplanetary species, no, intergalactic species. Type 1 would be interplanetary, type 2 would be intergalactic. So instead of going to India or going other side of Atlantic Ocean, you're going to go to the other side of the Milky Way, for example. Okay, great. So let's start our conversation with nuclear physics. So what is nuclear physics? Nuclear physics is the study to understand nucleons. What is nucleons? Nucleons is made of neutrons and protons. So nuclear physics deals with neutrons and protons, right? Okay, so let's understand what we already know to understand what we want to know. What do we already know? We know physical reaction. What else we already know? Chemical reaction. Now today we're going to try to understand the nuclear reactions. So example, melting, boiling, freezing. So for example, I give you 150 gram, all right, of ice, and I ask you to change it from solid to liquid. You're going to have to change it from solid to liquid. Solid to liquid is the physical reaction. Okay, so what are you going to ask? You're going to ask, all right, if you provide me heat, I would be able to convert it from solid to liquid. Ice is solid and, water is liquid. So, okay, then you're going to ask me to provide you heat, and I'll say, okay, I'll give you heat. How much? 340 joule, right? 340 joule over gram. So 1 gram, okay, 1 gram, so 340. So 1 gram, all right, 1 gram of solid, right? To convert it to liquid, you need 340 joule of energy. So how much? Gram cancel, so you have 50,000 joule. 50,000 joule needed, 50,000 joule of energy needed to convert solid to liquid, right? Ice to water. Okay, so this is an example of a physical reaction. Okay, so example of physical reaction is example solid to liquid. Chemical reaction. All right, let's talk about O2, H2O2, which is H2O, which is water. All right. So now in this case, you do not only you rearrange what? You rearrange the atoms. You get a new substance, right? This is a hydrogen gas. This is an oxygen gas, and you get a new substance, and that is water, right? And if you count the atoms, hydrogen atoms, how many? 2. Oxygen atoms, how many? 1, right? Hydrogen atoms, how many? 2. Oxygen atoms, how many? 2. So this is not a balanced equation. So let's make it balanced. Let's multiply it by 2. If you do multiply it by 2, you have to multiply it by 2 as well. So 4 hydrogen atoms. All right. So now you have to multiply this one by 2. So 2 oxygen atoms. Now this one and this one balance, but hydrogen now lost its balance. However, if you do add a 2 over here, then what do you get? 2 times 2, 4, right? Then you have this one and this one balanced. So you started with 6 atoms and you ended with also 6 atoms. Right? However, you rearrange the atoms. Okay, so here comes rearrangement. So you're going to add that over here in chemical example of chemical reaction, which is hydrogen gas plus oxygen gas become water. All right. In this process, rearrange. Here we're gonna put rearrange here. Rearrange. No, rearrange. Yes, absolutely. You rearrange the atoms. The nuclear reaction. The example of nuclear reaction would be example of atom bomb, nuclear power plant, and of course you have sun. Okay, the sun, interior of the core, the center of sun, fission. Okay, so this is fission and this is fusion. Okay, very nice. Okay, and rearrange, yes. Okay, now we're gonna see the new substance. Yes. Oh, this is now, of course, new substance. Yeah, hydrogen and oxygen become a new substance. Right. Okay. Yes. New element. No. No. Yes. And this is done by decay. Okay. Now, what else we gonna add to our list? The role of E equal mc squared. Okay, the rule of EMC square, now none, over here few, little used. Okay, and then how many forces, fundamental forces, how many fundamental forces involved with this type of reaction? None. We'll say here internal molecule. Okay, internal, and this one is Fe only, and this one is Fe, strong nuclear force and weak nuclear force. Okay, and that takes us to our next thing, and that is a nuclear reaction. So what is then nuclear reaction? And why we need nuclear reaction? Let's start our conversation with this. I have this. What is this? This is an helium. This is an helium nucleus, right? What is the problem of a helium nucleus? It has a problem. What is the name of this arrow? The name of this arrow is, of course, Fe. What is Fe is doing? Repulsive force, Coulomb force, we call it. repulsive force or Coulomb force. Now, why then nucleus is stable? If it wasn't stable, nobody would be stable, but everyone is stable. Why is that? Because of this arrow. And this arrow, of course, is bigger in magnitude than the other arrow. So what is the name of this arrow? The name of this arrow is, of course, a strong nuclear force, a strong nuclear force, and a strong nuclear force. So there is a tug of war between the Coulomb force and a strong nuclear force. And who is winning? A strong nuclear force, thank God. So that's the good news. Good news is a strong nuclear force is winning, so that we are stable. But bad news, all good news comes with bad news. The bad news is a strong nuclear force only works within 1 femtometer from the center. And 1 femtometer is a femtometer named after Enrico Fermi, who invented the atomic bomb because he discovered the idea of weak nuclear force. Okay, so weak nuclear force provide the support to those nucleus which is just too fat, right? Because whose size is bigger than 10 raised to negative 15 from the center. So if you are in nucleus, and how many nucleus? There are, I don't know, 118, but okay, so there are 118 elements, right, on the periodic table. And 118, they all did not bond at time zero. At time zero, we are talking about Big Bang. Only 2 elements formed, hydrogen and helium. And every other element, okay, 92 of them are naturally occur element. 92, okay, of them born after the Big Bang due to fusion. All right. Okay, so now all other element, okay, that's beyond the bismuth go through a nuclear decay. Why is that? Because their nucleus is bigger than 10 raised to negative 15 meter. So a strong nuclear force cannot offer support, because a strong nuclear force only work if your nucleus is small, and that is 10 raised to negative 15. But the bad news is not every single element has 10 raised to negative 15. Some of the element like bismuth or uranium just have too many protons, go way beyond 10 raised to negative 15 meter. So they need support. And this support provided by who? Weak nuclear force. Weak nuclear force allow them to decay, to become more stable. Their size getting small and small and small and small. And they want the size 10 raised to negative 15 so they can get support from a strong nuclear force. Until they get that small size, they keep going through the decay. All right. So what does that mean? That means there are 3 types of decay. Okay, so decay. Okay, so why decay? Nuclear decay. Two types of elements going through the decay. One, if you don't have same number of protons and neutrons, and number 2, if your nucleus is just too heavy. Okay, so we're going to talk about 3 types of decay. One is alpha decay. We're going to call it alpha decay. One is beta decay, positive beta decay. One is negative beta decay, and one is a gamma decay. All right, alpha decay. Let's talk about alpha decay. Alpha decay, what do you gain or lose? Alpha decay, all right, you lose what type of elements go through alpha decay? All right, type of elements that go through alpha decay is well, if your nucleus is just too fat. For example, alpha decay. So let's go over alpha decay now. If your nucleus is too fat, you go through alpha decay. And alpha decay, your nucleus is too fat. and then you lose a helium. Losing helium means you're losing a 2 proton and 4 particles. That's what you lose. All right, you lose a helium atom and 4 particles. Now let's give you an example. Uranium 238 go through alpha decay. What is going to happen if uranium 232 is going to become smaller? Let's see how small. It's going to become X. How is that? Because it's going to release a helium, which is 2 proton and 4 particles. 292 minus 2 is 90, and this is 234. So 234 plus 4 is 238. 2 plus 90 is 92. So what is X? X is thorium. So this is a little bit more stable, getting closer and closer by going through the decay. Alpha decay is getting closer and closer to 1 femtometer, 10 raised to negative 15 meter. Once it accomplishes 10 raised to negative 15 meter, it gets support from a strong nuclear force, and that's the goal. Okay, great. So that is alpha decay, right? Good. Now we're going to get to see a beta decay. Alpha decay, an example of alpha decay would be the medical image. Medical image use the alpha decay. Now let's see beta decay. Okay, so we finish alpha decay, so you're going to erase alpha decay. Now let's go over beta decay. There are 2 types of beta decay. Beta decay. So let's do beta decay. There are 2 types, beta minus and beta plus. Okay, so what is beta minus? Let's see. If you have, let's say, carbon 12 not going to go through any decay because this is as happy as you can get. Okay, so carbon 14 will go through beta decay because beta decay is when your proton is not equal to a neutron. Then you go through beta decay. Okay, this is the different cause. The first one was when your nucleus is too fat, alpha decay. This is when your proton is not equal to neutron. Good. So beta decay, what is it? More neutron than proton. Okay, so what's gonna happen? One of the neutron, right? One of the neutron gonna become what? Convert to proton. Okay, one of the neutron gonna convert to proton. If that happens, then what? Then 6 becomes 7 and 14 remains same. So you no longer carbon, you lose the identity. You are a new element. What do you want to call yourself? A nitrogen. So hydrogen, helium, lithium, carbon, nitrogen, oxygen. So you become a nitrogen. Okay, but not by violating conservation of charges. This is complete violation of conservation of charges because you started with on the left hand side you have a neutral charge, on the right hand side you have a positive charge. Total violation of conservation of charges. Something has to happen, and emission happen. What type of emission happen? If you have a positive, then you must have a what? A negative. Okay, so emission of an electron take place so that a positive charge and negative charge, if you put them together, if you add them together, is 0, right? Positive charge and negative charge is 0. Okay, great. So now the left hand side is equal to right hand side. Great. Now this is called matter. So you have 7 minus 1 is 6 and 14 plus 0 is 14. So far so good, but scientists realize that if this is 100%, this is not quite 100%. This is not quite 100%. This is 99.9%. Where is the remaining energy go? It was so difficult for them to detect because it's so small, and that is antineutrino. Okay, great. And this is called a beta decay. What beta decay? Negative beta decay. Now let's see other type of decay, and that is positive beta decay. Negative beta decay has to do with matter. All right, formation of matter. Positive beta decay will create the antimatter, and let's see. C11 will create antimatter. How? C11 will go through, okay, there is more proton than neutron. Okay, as you see, this is an analogy for you to don't memorize. Okay, for you not to memorize, I'm going to use lots of analogy. So you watch this tutorial, you're going to remember everything forever for good. Okay. All right, so this is gonna go through a beta, this one minus, and this one is gonna go through beta plus decay. So we're gonna put plus over here, beta plus decay. Why is that? Because a proton, because too many protons, a proton's gonna become what? A neutron. So proton gonna become a neutron. Look at the symbols, okay. Now, then if a proton become neutron, 6 not going to become 7, 6 is going to become 5 because the other one, neutron became proton, this one. Okay, and that one is going to be the same. So carbon, in this case, is no longer carbon. This is hydrogen, helium, lithium, beryllium, boron. This is boron. Okay, good. Now, this is total violation of conservation of charges. And you cannot violate something to accomplish something. You have to do it legally. Okay. So, nature does its business as legal as possible. Okay. So, what is going on over here? The scientists observed that when the beta decay happens, all right, it also do follow the conservation of charges. And emission happen. What type of emission? Anti-electron. What is anti-electron? Anti-electron is, of course, positive. The electron is negative, anti-electron is positive. Okay, a positive charge. Good. Now, if you have a positive over here and you have a positive on the right side, so left side you have a positive, right side you have a positive. Oh wow, business as usual. Very good. Now 5 plus 1 is 6 and 0 plus 11 is 11. So far so good. But scientists observed that if this is 100%, this is 99.99%. So they had a hard time detect a neutrino. Okay. All right. Now it's balanced. Okay. Good. So far so good. Now, other type of decay. Now let's give you one more example, and that is cobalt. So let's say cobalt. Cobalt is, I believe, 28 cobalt. Right, cobalt 28 and 60, right? Cobalt 28 and 60. You have um, too many neutron, right? You have too many neutron. So too many neutron. All right. If you do have too many neutron, it's going to go to beta minus decay. So if that is the case, then your neutron going to become what? A proton. Okay. All right. So this is going to become a 29, right? Okay. And this is 60, still 60. So this is, I think cobalt is 27. Cobalt, nickel, copper, zinc is 27. Is 27. Cobalt is 27. So this is 28. All right. It's 28. So cobalt is 27. So this is what? Nickel. Nickel. All right. Plus, of course, you have 28 plus what is 27? Of course, minus 1. And this is 0. And of course, this is neutrino. So this type of beta decay, right? The one thing you're going to observe that at the nucleus gets excited. The nucleus of nickel get very excited. So what happens when you get excited? Look at the energy level for hydrogen atom, right? Energy level for hydrogen atom. If you are getting excited for this, let's say n is equal to 4 to n is equal to 2, right? If you are electron, you jump down, right? When you jump down, you release a photon, and we human perceive that as light. They come as a packet, E equal to HF, right? Good, because that electron is excited, so it's jumped down. Very nice. And this is the same thing. Okay, so what happened with this nickel now? Excited nickel. Excited nickel, which is 28 and 60, will go through a type of a decay, and that is called gamma decay. When it goes to gamma decay, right, it is, right, it does not lose any particles or gain any particles. It only emit energy. in the form of gamma ray. So let's put all those together. Okay, so now you have, now let's say I'm going to put a sheet of paper. Okay, this is just a sheet of paper, aluminum, and then I'm going to draw a lead. All right, so if I shoot alpha particle over here, so alpha particle is, what happened alpha particle? Alpha particle is not very thin, it's very thick. Why is very thick? Because it's helium, right? Okay, so this is alpha particle. Alpha particle can go through only the sheet of paper, okay? But it cannot pass through aluminum, okay? It can go through only the sheet of paper. A beta particle, if I do beta particle, it can pass through the sheet of paper. It can pass through the aluminum as well, but it cannot pass through the lead. However, if I do the gamma, then it can pass through the lead. So alpha particle use the medical image, right? And the beta particle use lots of radiation therapy. And then gamma ray use in they call it uh, the surgery, gamma knife surgery. Gamma knife surgery, okay, so I'm going to write it, gamma knife surgery. Gamma knife surgery is in the brain. It happens in the brain when the brain has a tumor. To remove the tumor, they use, okay, so this is brain tumor, and they send the gamma ray from all direction, right, to remove the tumor safely. Because gamma ray is so small, how can I draw it? So if I draw it, so this is radio and this is gamma. Gamma ray energy is so high. Energy is so high because frequency is so high. All right. So for example, alpha, if someone shoot alpha decay, all right, it cannot penetrate through my skin. It's going to bounce back. If someone do beta decay, lots of X-ray they use, X-ray, they use beta decay, right? It can penetrate my skin and it can go to the bone, but it bounce back from the bone. Okay, so that as much as beta decay can do. Now the gamma, all right, the gamma ray, when someone shoot gamma ray, then it can penetrate, it can go from this direction and come out without doing any harm to my brain. Okay, that's gamma ray. Gamma ray can go from one side of the human head and come outside from the other side of the. So what would be the treatment? What would be the application of gamma ray? The gamma ray application would be the gamma knife surgery. You know, the doctors sometimes use gamma knife surgery to remove the tumor, for example, from the brain. Okay, so these are the type of decay. Now we're going to go to fission. So what is fission? So what is fission? Fission is break. All right. Okay. Big nucleus become too small nucleus, and that is fission. For example, to do fission, okay, so you're going to do two example, atom bomb and nuclear power plant. You need only 3% enrichment. You need 90% enrichment. All right, atom and nuclear power plant. Okay, enrichment. Okay, so how can you do enrichment? That's the condition number one. Okay, you're gonna go find uranium. Okay, most of the uranium are uranium, okay, 238. You cannot do the fission. Fission doesn't work with uranium 238. It only works with uranium 235, but not easy to separate 235. Okay, it's so difficult, right? Okay, so if you try to separate, it's like climbing up a mountain. The more you go up, the more difficult it becomes. But let's say if you do somehow, if you separate, if you have a 90% enrichment, all right, and then we're going to call it uranium 235. Uranium 235. 92 makes it uranium. Okay, and uranium is already what? Unstable. Why is that? Because with all the difference in protons and neutrons, as you see that, it already fact all the differences between this is unstable for two reasons, two fact, and the differences between neutron and protons. Okay, now if you add one more neutron, is gonna give up. Okay, so if you add one more neutron, it's going to give up. If you bombard it one more neutron, it's going to give up, and if you add one neutron, it's going to give up, and it's going to split into two. Let's say strontium and xenon, and xenon is 140 and 54. This is probably 36, 38. And this is okay, this is 92. Okay, let's see, 2 3 92. Okay, 232. Okay, no, this is not, this is 140. This is okay, I believe this is right. Okay, all right. So now what happened when you bombard a nucleus of uranium 235 with a neutron? It gave up. It was already unstable. Now it's going to become more unstable, and this is split into two: strontium and what? Xenon. We're going to, instead of calling it strontium, we're going to just put it like this, and we're going to put it like this. All right. And okay, when they split into two, okay, there would be an extra mass, and that extra mass will release the energy, and that energy would be what? E equal mc squared, right? Okay, what this extra mass will do causes the extra energy. Now this reaction, okay, is not a chemical or physical reaction, it's a nuclear reaction. Why is that? Because a new element born. Okay, a new element born. There was no new element born over here. O2 plus H2 is equal to H2O, right? No new element was born. Here, the new element born from uranium to strontium and xenon. Completely different thing. Completely different. Okay, very nice. Okay, now to do that, it also emit additional neutrons. How many? Let's see. Okay, 54 plus 38 is 92. Okay, 4 plus 8, 12. 4, 9, so 92. So this is nice. So this one works out well. Okay, 140 and 92. So you have 2, you have 3 and 1, 2. So 3. So 3 neutron. Okay, it releases 3 extra neutron. That extra neutron will what? Bombard this 3 extra neutron will bombard this again, and there is no guarantee that it will get what do you call xenon and strontium. It could be krypton, it could be barium, it could be anything. It could be 3 neutrons, it could be 5 neutrons. Okay, and it's going to keep happening. And if you do not absorb this neutron, okay, If you do not absorb this neutron, then you get uncontrolled chain reaction. If you absorb this neutron, if you absorb these neutrons, then what do you call control chain reaction? Control chain reaction give you something called nuclear flint. Uncontrolled is going to give you something called atom bomb. If you let it go, then it's going to create uncontrolled chain reaction. Every chain reaction will cause extra mass cause extra energy, okay, I will add, and within a fraction of a moment you have energy, and that is creating from very small mass. You have energy that is equivalent to E equal mc square, and c is the speed of light, and that is atom bomb. Okay, great. Now we're going to go to fusion. Okay, so fusion is just like opposite of fission. Fission is when the big nucleus is split into two smaller nucleus. Now this one is two smaller nucleus joined together to become a big, to emit energy in the form of gamma ray, who is what fueling the sun. Okay, so what is this example is sun. Sun. Okay, so this is Earth, right? Okay, and what is this? Fg, right? Fg. So what keeping us to the ground is Fg. All right. So then the sun, if it is sun, let's make it now sun. Let's call it now sun instead of Earth. So this is Fg. Now who is fighting with Fg? And that is fusion. Fusion is fighting with Fg. All right. So this is fusion. If there is no fusion, then what happened? Then the sun will become like this. Fg, Fg, Fg from all direction, and is going to crush. All right, and sun going to explode to supernova, and then that's it. The sun will turn to something called black hole. Okay, so there is a continuous fight, just like in our nucleus. Okay, in our nucleus there is a fight between electrostatic force and strong nuclear force, and in the sun there is a continuous fight between what? Gravity and fusion. Good. Now this fight, who wins? Well, for our sun, we like to believe that it is fusion. Of course, it's going to be fusion, but is fusion winning forever? No, there would be a death to our sun, and once our sun die, and then our planet Earth will also die, because we're going to realize that 8 minutes from the time when the sun died. Okay, great. All right. So what giving fusion? Two small nucleus make it a bigger nucleus. So let's say both of them hydrogen. One is the hydrogen atom, one is the hydrogen isotope deuterium. Okay, giving what? Giving what? 1 plus 1 is 2, and 2 plus 1 is 3. So this is helium. And of course, all right, it really is energy in the form of gamma ray, which is fueling the sun. Okay, what about helium? Two helium join and is going to give you beryllium, right? 4 and 8. And of course, there would be an emission of a gamma ray. So we know the alpha decay, we know the beta decay, and we see the gamma decay. All right, gamma decay is emission of photon in the form of high energy. Okay, and that is energy. That is energy. Gamma decay is just energy. All right, great. Now, if this is going to happen, then why our sun ever die? Okay, so now first let's see, let's draw this one positive, and then this is positive. This is hydrogen, this is hydrogen. Okay, how you can make a reaction between these two? Because there is a repulsive force. However, under extreme condition you can do that. And if it is sun, there is extreme condition. What is the temperature? Temperature is 15 million Celsius. What is the pressure? Pressure is 3 times 10 raised to 16 Pascal. And what is the density? Density is 150 gram per cubic centimeter. That's why fusion is almost impossible in our lab. Why? 15 million Celsius temperature is insane. That's why fusion is so difficult to do in our lab. Okay, that's what you needed to fuse between these two. Okay, say if you get that, and that extreme temperature only possible in the core of the sun, not on the surface of the sun. On the surface of the sun is like 6,000 Celsius, which is the core of our Earth. So surface of the sun is like core of our Earth. No good, not enough temperature for fusion. So core of the sun is enough temperature for fusion. Okay, if you do have, then you have a extremely high speed between these two. Under this high speed, they come close, they come close, they come close, and the distance become 0. If the distance becomes 0, then they fuse, and that fuse led to emission of high energy in the form of gamma rays fueling our sun. That, okay, our sun can fuse hydrogen, helium, lithium, hydrogen, helium, lithium, beryllium, boron, carbon, and cannot do more. But some other stars with higher temperature can fuse more, up until iron. So when it is go to iron, then what happens? You cannot fuse iron because iron is the most stable element. If you try to fuse iron, it becomes even more stable. So what happened? You cannot provide the fusion anymore. If you cannot provide fusion anymore, what happened? Then you become sun with only this. For how long? For not long, because you're going to collapse. And that is what we call supernova. We're going to stop here. So I'll see you on Thursday, and I hope you you win, and you win the Einstein competition, and you take the Einstein home. And it has been a pleasure to teach you physics. I hope you'll fall in love with physics. And I'm sorry, this is your last assignment. Without further ado, I would like to wish you a good luck with your academic endeavors. And I hope you will unlock the secret of fusion to make us not only type 1 civilization, type 2, or even beyond type 2. Take care, everybody.